Thank you so much for that introduction, Raleigh. I am so excited to be here. As she said, my name is Amy Pastor. I'm Vice President of Sustainability for EXP. I am an engineer, but I am not a geotechnical engineer. So I would like to start that by saying my area of focus is sustainability. So I worked with all of our amazing geotechnical engineers and our concrete specialists to put together and author this report, do the studies. So I say that because when you start to give me questions later, if they are super technical about the geotechnical properties and some of the sample, I will divert those to either other specialists in the room or take them back to my team. But if you have questions about a lot of things that Raleigh was introducing about with those greenhouse gas emissions, the transportation, the impacts on the quarries and the pits, I'm your girl for that. So a little bit of background for me, I am a mechanical engineer. My focus was always in buildings. And about 5 years into my career, I realized how wasteful we were with cooling and heating systems, with the water use in buildings. And I completely switched my focus to focus only on sustainability. So I've been doing sustainability for 15 years, and I haven't looked back since. And mentioning about the ESG report, EXP is a 4,200 person engineering firm, and we have in the last 5 years we're all in on sustainability. We're writing an ESG report, trying to reduce our own emissions, looking at our fleet vehicles and trying to walk that walk. So it's not just the projects we work on, we really want to be part of this change. So I'm really excited to be here to talk about what is truly a passion of mine in saving the planet and reducing these greenhouse gas emissions through our industry. So first, we can't do this without our sponsors. I'd just like to give a thank you to those who have both financially and in kind supported the studies and the efforts that went into this, this report that is part of, you can't see, I already failed with the two slides, that with the advocacy of this initiative. So whether it's these workshops we're doing at various municipalities or through conferences or speaking engagements like this, we're just very thankful as we move towards a more sustainable future. So the three main objectives guided our approach for this project. We realized that the importance of cost and quality have on wide-scale adoption. So we did our research, doing a lot of existing use cases and determining if the quality of the product has withstood the test of time, and then more importantly, the heavy traffic. So we're gonna look at a couple case studies that do all the way from residential all the way up to airports and how it has withstood the quality of time. So as we have this continued move towards a more sustainable, reliable, and resilient future, it is important that the materials we use in our infrastructure are more sustainable, but also economical. So our owner says if it's not affordable, it's not sustainable. And that really is true because we can't be putting, we have to find a solution that is economical, but also sustainable for just to continue to do that and work for our projects. So through this initiative, it is important we continue to support the adoption and wide-scale implementation of the use of RCA as efficiently and cost-effectively as possible. So let's first talk about sustainability benefits. You had already pointed out that the multiple articles discuss the limit amount of natural virgin aggregate. So whether it's the impacts of a quarry being shut down or the fact that there was a couple articles I read about non-renewal on leases, so they're just not going to renew the lease on the quarry. But the fact is that no more material could come from some of these pits and quarries, or the fact that we do have to source them from farther away, which is going to increase the transportation costs. So those same studies actually pointed to the availability, and it's a lot closer for the location of crushers or from suppliers who do have RCA readily available to transport to a construction site. So now you have this recycled material. It's at a location that is much closer to your site, and that gives you multiple paths to reducing those critical greenhouse gas emissions for the full life cycle of the material and the process. So we also add to the list of benefits diverting aggregates from the landfill, because usable quality construction and demolition waste, so that's C&D waste, we really need to redefine that. And that's when we're talking about it in this context, because sending materials from a demo to a landfill is essentially sending aggregate to a landfill. So we have to really redefine that when we're talking about this in this initiative. So here's where I within the sustainability world, you hear a lot of talk about greenwashing, and it's because people put boundaries around things, and they'll say, well, I'm net zero for this little boundary. But it is important to understand the boundary in the context of how we present these results. When we get to the very end, you'll start to see what the conservative estimate for savings is. But I want to put and talk just briefly about the boundary of our calculations, because we did want to give a conservative energy saving and greenhouse gas emission savings that could be just the number you throw out to a client or in an event. So when we talk about extraction from the quarry and the C&D waste, studies have shown that there is actually a reduction in the greenhouse gas emissions and actually a cost savings in selecting RCA. But the reality is, to make the calculations work, you still have to get the aggregate from somewhere. So everything on the left-hand side, we've eliminated from that saving because it's too variable. We've assumed that whether it's from a quarry or from a demolition site, the material still needs to be transported to the processing plant. So that is going to be a variable, and we didn't want to say that it's always going to be better for one or the other. So based on our research, it generally leans more favorably towards RCAs. But again, I just keep saying, as it's variable, we wanted to exclude it from our calculation. And then similarly, from the plant to the construction site, it still has to get there. All of the studies have shown that the crushers can either be on site or they are closer to locations. But again, it has been considered the same, and it's been negated from the calculations and the savings that we do project later. So here are some of those transportation values we like to see. So this is from an OSSGA report using the map of the quarry locations and determining the average distance from source to site. So for every kilometer traveled by the fleet transporting the aggregate, it's nearly 2,000 liters of diesel fuel consumed per day, and that's about 5 metric tons of CO2. The study did show quarries are between 35 and 70 kilometers from the site, seems to be about the average. So when you start to look at what the impacts are from fuel consumption and greenhouse gas emissions, it's anywhere from 69 to 148,000 liters of diesel fuel, and then the CO2 emissions are about 188 to 400 metric tons per day. So think about that. That is per day, the transportation of this aggregate to the sites. So with an understanding of the sustainability benefits, we wanted to dive further into the use of the materials from a quality perspective, and this is where my geotechnical team and our testing teams came in. And then also looking at the standard specifications and what is actually being used and what is defined for Gran A, Gran B types 1 and 3, and then Gran B types 2. So from the municipal spec 1010, both of these these are both from 2013. I know other areas of the spec have been updated, but right now both versions still reference April and November of 2013. And you'll see that Gran A is up to 100% RCA and up to 30% RIP. And then the same goes for Gran B's type 1 and 3. Type 2 does not allow recycled material. And then when we look at the provincial spec, type 10 also, does not specify the RCA content for Gran A and B types 1 and 3, but does allow up to 30% RAP, and that's that far right column for you. And then similarly, Gran B types 2 does not currently allow recycled material at all. So the good news. We have seen and have these really great recent examples of the use of Gran A materials in multiple highway or sections of roadway. So ranging from 1,000 to 47,000 tons, there are projects large and small. And then Gran A RCA still came in economically viable solution. And you can see in that case, and we'll show you in the next series of slides, the estimated cost savings when we actually go to that recycled material versus the use of the natural aggregate. So the next grouping of slides are just some project examples, and then we really want to highlight the key metrics and point out the benefits that you'll see here. Highway widening, including the center barrier wall replacement from Major Mackenzie Drive to King Road. So this is a project, Highway 400 from 2017 to 2021, and recycled aggregate was used to replace both the Gran B and Gran A aggregate, and then a total quantity of 300,000 tons with a $1.2 million cost savings. And you can see that distance from site. So I'm gonna talk about cost savings again. If it's not affordable, it's not sustainable. But it's also, when you start to look at this, you have to start looking at that transportation value. Because one thing that this study didn't talk about is the cost of carbon. And in the future, if you are going to be limited to an emissions from a project or a site and you go over that threshold, we're starting to see that you may be penalized because you've exceeded your carbon values for a project or what you need. And I mean, the value varies from anywhere from $500 to $205 or $50 to $205 per ton is what we're seeing. So just to kind of put that in perspective, when you start to look at why we keep showing the distance from the site, it's because those transportation emissions are probably the largest factor that you'll see throughout these slides. So we can even go back in time. Now we're looking almost 50 years to the Eden Expressway in Chicago. This was the first major US urban freeway that was completely reconstructed. So completely reconstructed from scratch. And it was also the largest highway project on which concrete recycling had been used up to that time. So the Illinois Department of Transportation used they used RCA in the base layer and fill applications, and it was nearly 350,000 tons of old pavement that were crushed on site, with about 85% of the RCA being used in those fill area, and then it was 15% used as a 3-inch unbound aggregate base. The asphalt treated base and the 10-inch continuously reinforced concrete pavement were also placed over the RCA base. The estimated fuel savings, as you can see here, is 200,000 gallons that would have otherwise been consumed in disposing of that, taking the crushed the old roadway off-site and then taking it off and then bringing in new virgin aggregate. So it was about 200,000 gallons of diesel fuel that were actually estimated to be saved through doing this process. So sticking with just a couple other roadway projects, the Illinois State Highway Authority used RCA and base materials for a decade and saved more than $61 million. So that's a pretty incredible and impressive savings. An 18-mile project in Minnesota saved 150,000 gallons of fuel, and it was about 27% in project costs. And then finally, a 1.5-mile roadway in Wisconsin projected savings of $250,000 over the project life. So moving away from highways and then just looking at large scale, airports, heavy airplanes being on those roadways. So it's beneficial in more than just highways. And there is precedent from the use of materials in airport projects. So this is just an early example of Pearson's airport, the old Terminal 1 decommissioning and demo. It allowed for over 253,000 tons of recycling on site. So again, we have this history. The airport's still there. Yes, they've done upgrades, but it has withstood the test of time, and I keep liking to say traffic. So this is the Pearson Airport Runway Rehabilitation Project, the most recent one. And the total estimate quantity of concrete diverted from the landfill was 25 million kilograms, or 55 million pounds, because that crushed concrete from the runway pavement was used as a subbase and base materials, and recycled milling asphalt materials on approach runway roads in the vicinity of the roadway. So this was the second busiest runway, and through this initiative, it's actually going to extend the life of the runway. But I really want to point out, I have a quote here. The sheer volume of concrete used in the project added up quickly. An estimated 39,000 cubic meters of concrete was used to reconstruct the roadway, which is the equivalent of 16 football fields. And that's just, and when you start to talk about it in that mass quantity and how much you have saved by reusing that concrete, it's very, very impressive. So we can go back further into the mid-90s, where the first use of RCA as a road-based material in Toronto's history was reported. And the picture on the bottom right is from 2022, and you can see that there were 0 structural issues in the pavement. And it's still, we actually did the condition assessment. Pavement is still in good condition, no structural failures, and it has been proven to stand the test of time, and I keep saying, and traffic as well. So from residential roadways to industrial subdivisions with heavy traffic, these engineering projects continue to uphold conformance with specs and withhold the test of weather too. So we've talked a lot about traffic, but weather is also a concern. Runoff from ice to storms. And then you can see that this construction year was over 4 years in different layers of pavement and the different types that were used. But we did do a test. This was back when it was originally constructed, and concluded that the 19 millimeter and the 50 millimeter RCA samples were in conformance with the specifications at the time. So in this example, we really had great information not only on the quantity used, but then the cost savings per ton. So we've talked a lot about quantity. Now we've started to talk about greenhouse gas emissions, getting into that financial information. So the quantity of RCA, Gran A and B, was 13,000 tons, which was split about 33%, 66%. And it actually estimated $150,000 in cost savings by switching to that material. And that equated to about $11.50 per ton. And then finally, I just want to wrap up with a couple ongoing projects. So this is the Finch light rail we're talking about, a P3 project designed here in Toronto where RCA is used for various applications. So not only is there a cost savings, but again, we start to talk about those greenhouse gas emissions and keep reiterating the fact that the distance from the crusher to the project versus the distance from the quarry. So in this instance, again, it was less than 10 kilometers. And then the contractors were also, I have a little note here in my slides, the contractors were permitted to dispose clean concrete and asphalt locally. So it also saved on the disposal, transportation costs, and the emissions. So those are the projects that we presented were from our literature review section, meaning that that was all the history. So we wanted to start the study and say, you know, has there been history of use? Has it withstood the test of time? Now we're going to go and do our own samples because, you know, we want to do our own research. We want to ensure that we had our own data to continue with our study. So in August and September of 2022, we collected 9 different samples. 6 were Gran A, RCA 1010, and 3 were Gran A native. The yard addresses and sample collection dates are listed on the table for reference. And can we leave these slides behind for everybody? I just don't know if they're too small for everybody to see. But they are listed on the table for reference, along with samples that were taken from each of those piles. We did document with photos that are included in the full couple 100-page report that was associated with these studies. So the first test that we did was gradation. 8 different sieve sizes were used for each sample, and then the acceptable limits are listed for reference. And just so you know, the most important thing here, in every sample collected, 100% passed through the 26.5 millimeter sieve. And then as you go down in size, the thresholds also went down, but every single category, and you can analyze that chart, it all passed at 100%. So and that was 9 different sample sites. So after gradation, there was also lab testing for the physical properties as compared through the specified values that are also listed in this table from the specification. So we are engineers, and just because it wasn't in the spec didn't mean we didn't want to test it, so we added a few extra in. And if it didn't have thresholds, we actually just made note of what the values were, just because we love numbers, and the more data, the better. So as you can see in the column on the far right, anything that had thresholds for passing, it 100% passed. So again, we've now looked at 9 different samples. Everything is passing quality, and also now we're looking through gradation. So I know that we are coming up on questions here, and I want to wrap up our presentation to come back full circle to what my passion is, which is the sustainable aspects, and the importance of this circular economy and life cycle analysis to promote this cultural shift from use of natural aggregates and natural materials to recycled materials. So I talked earlier about those calculations for transportation, and I talked earlier that the transportation numbers were this wild card because it's a variable. It's based on where your project is. If you happen to be right next to a quarry, then maybe the numbers work out in favor of that. But we did choose 4 projects and said we have the actual numbers, how far they were from the crusher and then also to the quarry, and wanted to do a deeper dive into the analysis. So let's check it out. We talk about the cost benefits. These 4 project examples, the average dollar per ton savings is about $8 so whether you have 7,000 or 100,000 tons, you're starting to look at, across these 4 projects, $1.4 million in savings just from these 4 examples. And then the distance from the crusher to the site was always closer than the pit to the quarry. So in the Brampton example, it was 42 kilometers, and then in Vaughan over 100 kilometers. So you start to see the benefits from a cost perspective and then also the distance. So here is that big colorful flow chart that I had in the beginning. Is this summed up to the actual cost savings and the emission savings and then the energy savings associated with the process for taking that aggregate and putting it on site. So we did use some additional research. I don't have it up here just because I want to save your eyes from the tiny numbers. It is all in the full report that is on TARBA's website. But the breakdown of this chart is just to show the savings from its process energy and then the carbon emissions less those transportation. So that's just that middle of that flow chart. Concrete from C&D waste carried the lowest energy and emissions value per ton, and then if you look with untreated material having the highest in both categories. So based on this information, we can firmly say and predict that a project is going to have anywhere from, it's a 25% savings in energy per ton of aggregate and a 46% from greenhouse gas emissions. And that number is only going to go up if you prioritize having recycled aggregate closer to your site as best you can. And so this is exactly what we see. I took those 4 examples where I did a deeper dive and started to show the savings. So we knew the distance from the site. I'm trying to look, my eyes are so bad. So another interesting fact, I just want to point out that we didn't want to make this just make it work. If you look at the processing, you'll see that the RCA processing number is actually higher in every single case. And why is that? Because not all construction and demolition waste is usable. So there is a heavier, intensive process at the plant to actually sort through that because we don't want it to impact quality. You can't just throw everything in there and you have drywall and all this other stuff. So even with that, we see that we still, it's over 60% in every scenario. We are still seeing based on the 4 examples that we used. And I like to throw a little number. It's taking 189 passenger vehicles off the road. So if that helps people with, what does that actual metric ton savings equate to when we start to talk about emissions. So we do want to point you to some additional reading material, which is the quality control plan for RCA, and then it's also a best practices guide for recycling aggregates, both by our partners TARBA. And then this actually, our report can be found on TARBA's website, as I keep mentioning, and we can send you a link to that. So we've established that, and just in summary, we've established that there's a quality product available, and with the implementation of a thorough QA/QC plan, we have to have a thorough QA/QC plan in place to make sure that the product that you're getting to the sites is actually usable and it's not going to fail. The use of RCA projects, use of RCA and infrastructure projects throughout GTA and Ontario should be really highly encouraged, and we need to keep being advocates for this initiative. And if municipalities lead the way, standing behind their environmental commitments, others are going to follow. So we all have to do this. We all have to be part of the solution and no longer the problem. The product has proven to stand the test of time and weather. The first example we had was from almost 50 years ago, and it's still standing strong. And it's widely available, and it's economically feasible across the entire region, which has also been proven in our studies. So some next steps. This is part of, me being here is part of our next steps too. The report was issued in late 2022, and since then we've done a number of advocacy events with different municipalities, different cities, different conference events, but it's really just continuing to advocate and show these numbers because there's proof in the numbers. We've been actively circulating the QC template plan because, again, we keep focusing on quality. If the quality's not there, it doesn't matter if it's more cost effective. Then you're going to have to reinstall it, and that's not going to be cost effective. And then involving third-party consultants. And then finally, that big one is updating the municipal specs because it's far too often. Again, we were talking about this. If it's not in the spec, we're not going to do it. Just if it's in the spec, you're going to do it. You're going to have to do it. But it's going to take some advocacy to make sure that it gets into that updated spec that is now almost 11 years old. So we are doing our job, we are doing our part. I know you are doing the same, otherwise you wouldn't be here, and I do thank you for your time, and I'm happy to answer any questions.